In today's lesson, I'll walk you through building a portable distance measuring device. You'll learn how to compute the distance to an object using an ultrasonic sensor and display the measured distance to an LCD screen. Hey everyone, this is Joe Edgo and welcome back to Education is Life. Today, we're diving into Lesson 5 of the series, Level Up with Arduino Uno R4 Wi-Fi IoT Development Crash Course. Throughout this series, we will be using this 52Pi Cloud-Ready Starter Kit. And in today's project, we will work with the two key components that are included in this kit. An HC-SR04 Ultrasonic Sensor and an LCD1602 display. If you are interested, you can check out their website at 52pi.com or find them on Amazon. Links are provided below. Thanks again, 52Pi, for sponsoring this series. For this project, you'll need the following materials: an ultrasonic distance sensor, HC-SR04, an I2C LCD1602 display, a breadboard, some connecting wires, and your Arduino Uno R4 Wi-Fi. The HC-SR04 ultrasonic sensor is an affordable and widely used proximity and distance sensor. It works by transmitting an ultrasonic pulse, this is above human hearing at 40 kHz, and measuring the time it takes for the echo to return. This sensor is commonly used in robotics for object avoidance, parking sensors, security systems, and even water level detection. Now, the sensor itself is pretty straightforward. It has 4 pins, VCC for power, GND for ground, a trigger pin to send out the ultrasonic pulse, and the echo pin to listen for the reflected wave. To use the sensor, we'll connect the VCC pin to 5 volts on the Arduino, or 3.3 volts depending on the controller you are using, the ground pin to ground, the trig pin to a digital pin of the Arduino. We'll use pin 4. And the echo pin to another digital pin. We'll use pin 3. So, here's how the ultrasonic sensor works. The trigger pin only needs a quick 10 microsecond pulse to start the ranging process. The sensor then emits an ultrasonic wave, an 8-cycle burst of ultrasound at 40,000 Hz. This wave travels out from the transmitter, bounces off the nearest object, and comes back to the sensor. Once the receiver detects it, it then raises its echo pin as a pulse. Now, the echo pulse usually ranges between 100 microseconds to 18 millisecond duration. So, the time it takes for the echo to return is proportional to the distance of the object. The longer the echo pulse duration, the further away the object that is being measured. Please note that the operating range of this HC-SR04 module is between 2 cm to 400 cm, plus or minus 3 mm accuracy. However, its most effective detection range is between 0.3 meters and 3 meters. Now, to calculate the distance of an object, we use the formula. Distance equals duration of the echo pulse multiplied by the speed of sound in air divided by 2, with the speed of sound being approximately 343 meters per second, or 0.0343 centimeters per microsecond. So, for example, if the echo pulse reads 800 microseconds, then 800 times 0.0343 divided by 2 equals 13.72 centimeters. And this is the measured distance from the ultrasonic sensor to the object in range. Now, to make this distance measuring device portable, let's hook this up to an LCD1602 screen where we can display the measured distance. The LCD1602 is a popular 16x2 character display used to show basic text, numbers, and symbols. It has an LCD backlight and can display 32 ASCII characters in 2 rows. That is 16 characters on each row. The LCD1602 uses an I2C interface, simplifying the connections to just 4 wires: VCC, ground, SDA or data, and SCL or clock. This I2C module is the one responsible for converting the signals from the Arduino to the LCD. To connect the LCD1602, the VCC pin connects to 5 volts on the Arduino, the ground pin connects to the ground, the SDA goes to the SDA pin on the Arduino. This is the same I2C bus that is connected to pin A4. And the SEL goes to the SEL pin on the Arduino, the same I2C bus that is connected to pin A5. So to start using this LCD1602 display, first, we need to install the Liquid Crystal I2C library by Frank de Brabander. Then, include the library in your code with #include liquid crystal i2c.h. Now, create an LCD object of the Liquid Crystal I2C class, we call it LCD, and then we pass 3 arguments. For this I2C module, the default address is 27 hexadecimal. Please double-check your specific LCD's documentation for its address as it might be different. The second and the third arguments represent the number of characters and the number of rows respectively. That's 16 characters per row. Now, in the setup function, initialize the LCD with lcd.init. Clear it with the lcd.clear and turn the backlight on. To print on the LCD, we use the lcd.setCursor method to set the position. The first argument is the x-coordinate, which defines how many character positions from the left. This is zero-based. For example, if I want to start printing on the 4th column from the left, I'll put here 3. Then the second argument is the y-coordinate. So, 0 means first row. Now to display text, we use lcd.print, say Ultrasonic. And then on the second row, starting on the 6th character position, let's print Sensor. For now, let's try to upload this program to see if we can successfully print something on the LCD screen. And it works. So now, let's work on the code that reads the distance from the ultrasonic sensor and then displays the measurements on the screen. First, let's define 2 constant variables called echo pin at pin 3 and trig pin at pin 4. These are the pins we used to connect the echo and the trigger pins of our ultrasonic sensor earlier. Then, let's set the echo pin as input and the trig pin as output. Let's also have a short delay here of 3 seconds before starting the main loop. Now, here's how we calculate the distance between the sensor and an object in range. We start by setting the trig pin of the sensor to low to ensure a clean pulse. Then let's have a short delay of 2 microseconds before raising this pin to high. Now, let's set this trig pin to high for 10 microseconds. And then, set it back to low to start the ranging process. At this point, the sensor emits an 8-cycle sonic burst, bounces off the nearest object, and then comes back to the sensor. It then raises the echo pin of the sensor. This is the one that we need to measure in our Arduino code, the duration of the echo pulse. So to measure the pulse width of the echo pin and calculate the distance, we declare a float variable distance and then read the pulse duration using the pulse_in method. The first argument is the pin where we want to read the pulse. And the second argument is a value of either high or low. In this case, a high value means it waits for the echo pin to go from low to high, starts timing, then waits for the pin to go low and stops timing. The length of the returned pulse is measured in microseconds. So all we need to do is multiply this value by 0.0343 centimeters per microsecond, which is the speed of sound in air, and then divide it by 2. This calculation gives us the distance in centimeters. We can also convert this to another unit of measurement, such as inches. Let's create another variable called distance inches. To calculate the distance in inches, we simply divide the distance in centimeters by 2.54, since 1 inch equals 2.54 centimeters. Next, we'll display these measurements on the LCD. On the first row, we'll print distance in centimeters, and then display the distance variable. On the second row, we'll print the distance in inches, and that's it. One important note, it is recommended to use a reading cycle of over 60 milliseconds to avoid collision between the trigger signal and the echo signal. So, we'll add a short delay here of 500 milliseconds before the next sensor reading. Now, let's upload the code and see it in action. And there you have it, your very own portable distance measuring device. Now, let's build on what we've learned in the previous lesson about organizing our code. We can create a custom function to handle the distance reading and call it directly in our main loop. To do this, let's cut these lines of code and create a function called readDistance with a return type of float. The purpose of this function is to perform the measurement and return the calculated distance in centimeters. We'll paste the lines of code we just cut into this new function. Then, we'll add a return statement to send the computed distance back to the calling program. In the main loop, we'll create a local variable distance and call the readDistance function. The return value will be assigned to this variable. And that's it. Our program will function exactly the same. But now, it's more modular and organized. Thank you so much for joining me for the 5th lesson of this series, Level Up with Arduino Uno R4 Wi-Fi IoT Development Crash Course. If you enjoyed this video, don't forget to give it a thumbs up. It really helps. And if you're excited to learn more about Arduino, make sure to hit that subscribe button and ring that notification bell so you never miss an update. Feel free to share this video with friends who might be interested in diving into Arduino projects. The more learners we have, the more exciting and in-depth content I can create for you in the future. So, keep learning, keep experimenting, and always remember education is life. I'll see you in the next lesson. Happy coding!